Okay, good morning. Hope you all had a good weekend. There should be 3 handouts going around. One is the handouts for the lecture. I'll try to give one every class. There should be a homework assignment and a homework project. Homework assignment is basically it's exercises from the textbook, helping you prepare for the exams and stuff like that. The homework project, you would download a Linux kernel and then configure it and then do some experiments on it, right? And so many of you have installed some kind of operating system, Windows and stuff, but very few of you have done anything with Linux, right? So for the most part, it should be fairly straightforward, but if you have done anything with computers on anything, you will notice that things don't go the way you expect them to go, right? So we have the lab 208 for you to work on stuff. If you have your own computers, you're free to use those. And in general, if you wanted to go beyond what was asked, if you want to try something on your own, I'm all for it. Just let me know what you're trying to do and then go for it. So you don't have to follow exactly what I said mindlessly, right? So if you have a PC at home that you want to work on it and you want to try the same things, that's fine with me. If you want to use the one in 208 Cushing, the room should be open most of the time. I think after hours it'll be closed, and the code to enter that room is 2513. I didn't put it on the thing because I didn't want it to be that insecure, but it is a little bit insecure because it's being videotaped and it will be online. So if somebody wants to look at it, it's still there. So there are 6 machines plus 2 servers, EXP-DTP 1 through 6, which is available for our class. And the server one is Itanium, 2 dual processor, one is a quad processor server. That's also available. You're free to use those for the experiments. The details are it uses EFI, which is a different way of booting the kernel. So if you're not really sure on how to do Linux and stuff, you may run into problems with the EFI stuff, right? So if you know what you're doing and you're particularly adventurous, you can try the servers. If not, you have the 6 other machines. And the projects are a group of 2, right? So I hope you have a group partner. If you don't, send an email to the class mailing list to find a person to work with. And you'll hopefully have the same project partner throughout the course, right? And if you run into any problems, let me know. Suggest that you start as soon as possible because these things tend to get hairy towards the end, especially when everybody else is trying to step on each other's foot, right? So before you start working on a machine, use some convention to make sure that somebody stays off. I think a good convention is whoever is on the console gets to use that machine for how long they are. So don't try to remote log in. All of us have root privileges. You can do sudo to do something, so don't try to mess somebody else up because it's not helpful. Yeah?
The due date says September 9th.
Oh, fine. It's next Friday for the project. Yeah, the due date is next Friday. Week from Friday. Yeah, it's a week. It's next Friday. So get started and look through the thing. Basically, you would download a kernel and you would configure the kernel. There's a sort of graphical version of it if you do make miniconfig, and it gives you a bunch of options, right? I want you to go through those options and change one particular option, run that little program, and see what report what you find, and make a little conjecture of what might be happening, right? And in the lecture today, we'll be talking a little bit about what is really happening out there. It's basically the timer event of the kernel you are trying to configure. But this will get you a feel of what the things out there. So I'm not telling you exactly precisely how to go inside the menu to find the stuff. hopefully by looking at it, you'll see some of this stuff, which we'll use later on in the course, in more detail, right? Yes?
Is our module exam going to be next Friday as well?
I think it's next Wednesday. Yes, it's next Wednesday. The project's always due after the exams.
Okay.
Yeah, the exams will the model exams will be in class. I'm hoping for half an hour so we can discuss the solutions right after the exams. So, is that clear? So getting back to the lecture, so so far, in the last lecture, we're trying to kind of nail down what operating system is and what things it provides. And operating system manages resources and arbitrates resources. And we haven't, throughout the course, we'll try to figure out how it does that for each component. For now, it manages resources, right? So if it manages resources, you cannot let anyone or everything in the system mess with that management, because in that case, you can't enforce anything, right? So the way you enforce that is to have these, like, a protection boundary, sort of. If once you're inside the kernel, you can do whatever you want. Once you're the normal user, you can do whatever you want within your own process, but if you want to do something which affects others, you have to ask the operating system. And the way you ask the operating system, the only way you kind of go from the user to the system is through the system call. Right? So it provides one sentry kind of thing into the operating system. And every process, every request has to go through this one mechanism, right? And system call, we looked at the details. So you have system call number, and there's ways to send the parameters in and out of the kernel, but basically there's one entry into the operating system. And you can use that as system call in your C programs or any other programming language you want, or you can abstract it away and have systems programs which use these system calls to provide more functionality, and you build some things on top of it, right? So that's what we looked at. The other component which we kind of alluded to was operating systems tend to be large pieces of code, right? And how you organize them has implications on how well they are maintainable and all those things. So you can have them as one large spaghetti code, and usually that bigger code is highly unmaintainable. So typical operating systems tend to be fairly large. So you don't want to do that. So people have, over the years have looked at layered architecture where you define multiple different layers and you say each layer what it provides to the next layer. And if you have large number of layers, then each layer tends to be small, but the whole system becomes hairy. And if there's small number of layers, then each layer becomes complicated in the case of sort of like your Unix. And over the years, people have looked at microkernels where you tend to have, you're supposed to have extremely small, robust kernel and move everything out of the kernel, right? Move everything out of the protected domain. And it's supposed to give you all the stuff that you want, maintainability and speed and everything. And there are issues with each other's approach. Human beings code these things, so they tend to make these things not work the way you want them. The other way to add functionality is through modules or dynamic libraries. So that way you can add functionality to the kernel. So if you buy a new printer, it comes with its own DLL that you install into the operating system. And now that becomes part of the operating system, adding more functionality, which could be a good thing because now you're changing the operating system without having the source code. Could be a bad thing because now the operating system is as buggy as all these components to put together. Right? The stuff we didn't cover last class is the notion of virtual machines. This notion came about back in the mainframe computer days, where there used to be one computer for the whole university, and this was a way to make it look like there are multiple different machines that you can give to different departments or what have you, and have them run their own operating system on top of it. So the notion here is you have one underlying hardware, you run some software to make it look like you have many different versions of the same exact hardware, and you install operating system on each one of those virtual machines, right? Each one of them looks like they are independent machine. You can install any number of operating systems on top of it to make it look different. So you can have one machine and have the human resources and the teaching side of it and all those things use this virtualization, right? And have different operating system running on top of it. And as you may have imagined, this machine cannot be faster than the single machine. I mean, you're trying to switch the one single machine across these 3 different machines, but it gives you flexibility in terms of having different views for different users, right? And that's the notion of a virtual machine. It was popular in the days when machines were really, really expensive. And this is one way to share the machines. And it's coming back now for a different reason, and that's one of the reasons why I wanted to mention this. It's coming back in the age of data centers, right? You might have heard this term data center. If you haven't, most of the corporate computing, in terms of grid computing, all those things, companies rarely buy their own machines, in-house, put them, and then use them per department kind of stuff. They would want to have these massively managed big things called data centers, right? And they either lease it out to other companies or lease it out to the different departments. So for example, AOL has humongous data centers having thousands or millions of computers sitting out there for the different customers, right? Amazon and Google and all those things have these big things. So the way they operate is, if you as a customer say you want 1,000 computers or 10,000 computers, and if you pay me, I'll do something and give all the resources over to you. And when you're done, I'll take it and give it to somebody else. How good I do this decides how much I can charge you, kind of thing. And it's a really interesting way to get resources rather than buying your own machines and managing this stuff. So what happens is, if I'm the data center provider and I have 2 customers who are, one is Ford and one is GM, right? And they want to run their system to do whatever they want. I want to do the same kind of stuff I did before. I want to give protection. I don't want Ford to find out what GM is doing and so on, right? I could buy different machines. I could buy separate machines and say this goes to this company and this goes to this another company. But a more realistic approach is to use the virtual machine technology to make one single machine look like multiple different ones. So I can allocate a certain number of virtual machines to one and a certain number of other virtual machines to another company, right? So there's a lot of work going on in this particular area right now, grid computing and virtualization. We'll sort of look at it a little bit later on in the class, but this is something that you'll hear a lot more when you go into industry, right? So it makes it look like there are multiple different operating systems, multiple different machines on the same machine by trying to multiplex, by trying to make sure that a single CD will appear as multiple CDs on different operating systems, right? So here's a sort of a picture of how this happens. Over to your left, the non-virtual machine, you have the hardware, you have the operating system kernel sitting on top of it, and you have the user processors. But if you do the virtual machine, now you add a little virtual machine implementation at the bottom, right? And then you can have multiple virtual machines running on top of it. Each one appears like a machine, and you'll install a kernel onto each one of those, right? Each one of them don't talk to each other. I mean, they can talk to each other like as if they're independent machines, right? They don't share any memory. They don't share anything. They are independent machines. The only way you will know that they are virtual machines is if you look at the timing. There's still only one hardware, so you can't do something at the same exact time. You can't use a CD player for the same, one CD player across multiple machines at the exact same time. But for the most part, it's transparent, and you'll have multiple versions of it. And even when you don't do data sharing, this is an easy way to develop operating systems and stuff. So for example, for your course, if you want to install something and you want to crash the machine, this is an easy way to look at it. You can implement this and you can crash it. You won't destroy anybody else any other processes on the system. Most of the virtual machines tend to be resource hogs because it's trying to run more, trying to run 1 or 2 machines at the same stuff. So there are ways to make it a little bit better, right? But for using for this class, you need a lot of memory and a lot of CPUs and stuff like that. And there are other issues why we're not using it for this class, but that's a good way to use it. So even in the cases where you're not doing a data center, a lot of people like to do this because some of you mentioned that most of you mentioned that you were bitten by the Windows bug. Right? So if you run a virtual machine, you can run your Windows in a virtual machine. If it crashes, sure, just go back to the original state, and then you can keep going. Your machine doesn't crash, only a virtual machine crashes. And one of the popular virtual machines that you can buy off the shelf is made by VMware. I don't know how many of you have used the VMware software. So where did you use it?
Yeah, I use it in my dorm.
Okay.
Test software stuff with it.
Use the workstation version or the?
Yeah.
Okay. So VMware is, their main bread and butter is making these virtual machines. They have the workstation version, which is, like I mentioned, it's resource hog. So if you have 2 virtual machines, then it practically takes twice as much memory, all the resources. They have enterprise version, which is smarter, and it doesn't use as many resources. But basically, it tries to. So if you install it on Linux, right, then you can create virtual machines, and you can run Windows or whatever operating system you choose, right? And on the Macintosh, you can run virtual PC, which tries to do the similar thing, right? And you might also use the Java virtual machine, which tries to do the same thing. The Java virtual machine implements the Java virtual architecture on top of a host system. So that's one of the reasons why your software is portable, right? You write your code, the Java code, for Java virtual machine, not the underlying machine. So when you run a Java virtual machine, right, and you run applications on top of it, it's portable because you're running it on the same stuff on the top. Underlying, the virtual machine layer itself is different for different machines. So you can run it on Windows or Linux or what have you, right? But your user-written programs are running on the Java virtual machine, not on the native machine, and that's why they are portable. That's why you have security and all those things. So if you run different Java machines on the same physical machine, you'll notice that they don't actually share anything. If one crashes, the other one can keep going and stuff like that. And that's part of the allure of the virtual machines. And for the most part, the Java virtual machines have fairly decent performance, as good as the underlying machine. And there are other issues that we'll kind of mention in passing, which you will notice for your homework project. One is you want the operating system to run for a class of machines, not for a specific machine, right? So, for example, you want to know what kind of resources are there in a machine, what kind of a CD-ROM, what is their timing, and so on and so forth, right? So you could either write an operating system which is exactly tuned for a particular machine, or you can have it test out what is available and then try to make a guess on what the configuration is. Most modern operating systems would do the testing, right? And part of what you're trying to do for the project is trying to configure the kernel to see what it would test. You'll notice that you can turn off some sections. You can say, my machine will not have a CD player at all, so do not test for a CD player, right? That's probably not a wise thing to do because you won't be able to install anything with a CD player, but you can change it. You can say what it should test and what it shouldn't test. The more it tests, the more it takes time for it to start up, right? But basically the idea is when it starts up, it does a lot of testing. So if you look in the console, you look at the error messages, you see a whole bunch of stuff. It's probing each hardware. It's trying to figure out what is what are the capabilities, and what it can do. It'll also see what are the different device drivers have different bugs. So it's trying to figure out what's the version so it can react to it. And like any good software, it's good for the most part, but sometimes it doesn't work, right? And I think some of you mentioned that you tried to install Linux and your kernel did not work. Frequently it fails over here. It tries to find something, it doesn't exactly know what is going on, and you have problems. It's an interesting problem, and most of the solutions are kind of trial and error kind of stuff. The other problem that we won't stress too much, but it's a big problem when you're trying to actually do it, is how to bootstrap the system, how to start off from nothing, right? So you have your operating system somewhere, maybe in a CD, maybe on a hard disk somewhere. Machine starts up, right? Somehow it has to go from nothing to give control to your operating system. And once it gives control to your operating system, then you can kind of do some things, right? So there are a number of process steps it goes through before it gives control to you. And that's part of the bootstrapping or the booting problem, right? And there are many different ways of doing this, and you might have seen the boot prompts and stuff. You might have seen the EFI, which is I mentioned the Itanium servers, and also on the new Mac, Intel Macs, right? And the Macintosh uses open firmware, and there's a whole bunch of stuff, and there's a whole bunch of things that can either delight you or confuse you, right? But basically, all of them are trying to do is somehow get you from when you hit the power switch to the operating system, and they're trying to do different stuff so that the operating system can act better, right? So one of the stuff that they do is they try to initialize some of the resources, initialize some of the hard drives. So when the operating system tries to probe it, the BIOS itself would give it more information so it can proceed, and you can turn off stuff. So if any of you have gone through the BIOS and tried to turn off and turn on features, you would have noticed, right? And it's a constant battle on what should be done in the booting process and what should be done in the operating system, and you may have a lot of horror stories or good stories. But basically the idea is you're trying to do the stuff. And so the popular way to do that is to have a bootstrap loader, right? So the idea is the hardware knows magically how to get this bootstrap loader. So it expects the bootstrap loader to be of a certain format at a certain location exactly on the hard drive. So it doesn't have to search. So for example, you can say on the hard disk on sector 1 on this particular area, whatever program is there, I will first run. That's a bootstrap loader, right? And that particular program will know what to do next to load the next step, right? And that's one way to do that. The problem is you want this stuff to be as simple as possible so that the manufacturers can make these things where different people can install different software. And so when it starts up, it first goes to the firmware, which is on the hardware. Then it goes to this bootloader, loads whatever is in there, and the bootloader will know then what to do, and then it goes from there. Right? I'm not going into the details of this because the details are a lot gorier than what I mentioned here. But the key is the job is to somehow get the operating system to run, and off you go, right? So that's all the stuff I had about general about operating systems and general the high level view of operating systems and stuff like that. Is that clear so far? So we'll switch to the first module, what we're trying to look at, right? The first module is we're trying to look on how to manage resources for the CPU or the processing aspects of a machine, right? So the idea here is you want to share the CPU so that different users can use the same machine at the same time, or appear to use the same machine at the same time. So the abstraction we want to introduce, the abstraction we introduce is called a process, right? All of you have used process all the time, and process is basically a program in execution. So if you have a program on a CD or a hard disk or what have you, once the program is running, it's called a process, right? And with this abstraction of process, you can associate resources to it. You can give stuff to it, and one of the stuff you give to it is a CPU, and you can do scheduling and stuff. But basically, a process which is a program which is an execution. So if you write a C program, compile it, and it starts to execute, that's called a process. And a process is much more than just the exact program, right? A process has a context. which is defined as by the program counter, which basically states where in the program it's running right now. So if you have a big program, the program counter defines what exact instruction is being executed for you. And there are other contexts that go with it. One of them is the register. So at any one instant, your process is doing a particular step, and the status of the registers in the machine status defines what exactly it's doing at that point, right? So that basically defines that if you freeze the program, if somehow you can stop time, right, that those two will define what exactly your program is doing at that particular instant. Then you have the stack and the heap. Stack for allocating, function return values and parameters and stuff like that. Sort of from your, you use them from your C program or whatever program you've written. And then heap for memory allocation. So when you do a malloc or similar calls, you want your process to get more memory. So the operating system has to make all these things happen. So it's not just okay to just take the program and run it. It has to give it some memory for it to run. And if it asks for more memory, you should be able to give it more memory, right? It also defines two sections, data section and text section. Text section is basically your program. So it loads the program off of your media into the text section, and it allocates global variables and all on the data section, right? So before your program can run, the operating system has to at least set up these stuff and give control to your to the program counter so you can run. And these processes go through different steps along the way, and they go through different steps because you want to run multiple processes. So you're trying to use the CPU as wisely as possible. So you want to say, if somebody is not using the processor, I want to take it away and give it to somebody else, right? And the reason why you don't want to use the processors, one of the main reasons is because you are trying to do I/O. If you're doing input output and it's tend to be slow, right, and you're doing nothing, you want to take the CPU from you and give it to somebody else. So this kind of defines the different states that the process goes through. I mean, the real operating system have more complicated stuff, but the high level, you are new, you are admitted into the system, right? You don't have to be admitted all the time, and that's part of the OS trying to figure out whether you should be admitted at all. If the system has too much load, if it's doing too much stuff, it can make you come back after a while. But for now, after it's admitted, you are in this ready state. You are in a state where you're good to go, but you don't have a CPU yet, right? At that state, you have all the heap and data and all those things allocated for you. You're ready to go. You're waiting there till some event happens, till the CPU is found to be free and it's ready to be given to you. Then you switched into this running state, right? In the running state, you have all the resources you need to make progress. You are running, right? And if nothing happened, if your program is very simple and you are able to finish everything within that instant, you exit the system by being terminated, right? Either gracefully because you call exit, or ungracefully because you did something wrong and you got a segmentation fault or something. So the process at least goes through, this new process, it goes to the ready queue, and it starts to run, and then it's terminated. But while it's running, there may be reasons why it has to go back to the ready state, right? One of the reasons I said before was because it has some I/O I/O process. It has to read something off the terminal. So while it's reading, right, it gives up its CPU, puts itself in the right queue to say I'm waiting for the I/O, and goes into this wait state, which means that till that event that it's waiting for happens, it doesn't make any progress, but it doesn't hold on to the CPU at all. So somebody else can run while it's doing that. It can also go there because of timer or other interrupts. You can go back to the wait state because something happened. And one of the other reasons is if you're using too much CPU, the OS might decide to take you off the list and let somebody else run, right? So remember, OS goal is to be a resource arbitrator and manager. So just because you're running, right, if it doesn't control how much CPU you're getting, right? Then you can hog up the whole machine. So the OS is constantly sitting there. So if it thinks that you're using too much resources, it can move you to the ready state and then push you back, right? So it can forcefully make you go to the ready state, or you may do something that requires you to go to the ready state. So so this is the life cycle of a process. You whenever the CPU is free and you're ready to go, you get to run, and different events will make you go to the ready state. So you cannot go back and forth between these states. The operating system keeps track of all the stuff for a process using a processor control block. It's a data structure that it maintains, which is the incarnation of a process inside the operating system, right? So it has information about the process state, about the program counter, registers, and so on. It has stuff about the memory management. It has stuff about the where the data section is, where the text section is, where the heap is, stack is, all information, accounting information, how much CPU used. Anything that you know about the process is allocated to this process control block, right? And the I/O status information. Yeah, basically, all the state of the process is incorporated into this process control block, and it gets allocated when you come in. When you come in as a new process, it allocates all the stuff for you, fills all the stuff that it can, in terms of text and all those things. So when you start a process, it has to first allocate you some text section, right? Bring all the stuff from a disk, your programs into the text section, set up some stack for you, set up some heap for you, fill out these structures, set the program counter, and you are ready to go. And the other things I kind of alluded to along the way was the operating system maintains lots of queues, right? Lots of queues where things keep moving. So in the state diagram we saw, you come in, then you go to this ready queue, then you go to the running, and so on and so forth. And those all translate to different queues. And basically, if a PCB is allocated to a particular queue, it's doing that. So if it's allocated to the ready queue, that means it's waiting for the processor. And then when it waits for a disk, right, it gets put on the disk queue. And when the disk operation is finished, some part of the operating system will take it out of the disk queue and put it in the ready queue, and so on. In SATA, this is how the graphical view of this. So basically, you have different queues, and each PCB corresponds to a different process, a different process running, right? So it could be on any one of these states, except in running, right? And the process scheduling, which basically tries to figure out who should run next. You can think of this graph as the one I was telling you a little bit before, right? So when you're running on the CPU, you may ask for I/O, in which case you put on the you make I/O requests, you put on the appropriate I/O queue. When the I/O finishes, you go back on the ready queue, right? If your time slice expired because you've been using the CPU for too long, you are put back on the ready queue, and the next one, when it tries to create a process, we'll get to that in a little bit, right? Depending on other policies, it may decide that if you're waiting for a child, right, it'll put you on a particular queue for that, or interrupts, right? Interrupt, either timed or whatever interrupts. So the operating system's job is to make this scheduler, make this stuff run so that everybody's happy, everybody's, for whatever notions of fair, right? So that's the main task of the operating system. So now it has different processes. It's somehow allocated this PCB structure, right? Its job is to juggle all these processes with, each process waiting for I/O and stuff. Each process is doing some things, and juggle them such that you have a good, useful system, right? And that's the primary task of resource management for the CPU. So you typically define this as 3 different set of schedulers. in terms of what their long-term goal is for the good of the system. So the first one is the long-term scheduler, right? Long-term scheduler tries to look out for the system in the long term to see how the system is doing overall, right? If it's being bogged down with too much work, its job is to even out the resource usage in the long term. So if the machine suddenly notices that there are 1,000 processes running, right, and 1,000 processes is a lot for normal machines, it can push back. It can say, no new processes till all this stuff clear out, right? And that's the job of the long-term scheduler. It's trying to look out in the long term how the system is doing, if it's being loaded or not, and it's trying to manage that. The short-term scheduler is looking at at the millisecond level how much CPU you have used, and then tries to kick you out and stuff, and it tries to move you through the system, right? So with these two, once you're in the system, you go through the flow chart we just saw. You go to the ready and run kind of stuff. So if the system is completely loaded for whatever reason, right, the short-term scheduler will keep letting you run and keep the system busy all the time. Whereas the long-term scheduler will notice this is happening and won't admit any new processes coming into the system. So you also define a notion of a medium-term scheduler, which says that, okay, the long-term scheduler messed up, it let in too many processes, and the machine is just dying. So it can swap things, or it can freeze some of the processes out, so to let the others complete, right? All the games you're trying to play here is to juggle the CPU across multiple different stuff, right? But if you have way too many things to juggle, nobody makes progress and the system just kind of dies. And the medium scheduler, if it notices something like that happening, would freeze some of the processes and let the others kind of complete, right? So this brings up one of the things that you should remember about operating systems, right? Operating system is trying to juggle all this stuff. It's trying to manage the processes, give the CPU to different processes and stuff, but it's not doing any more magic than what the hardware can do, right? So if there are two processes and it's trying, and both of them want CPU all the time, it's trying to give it one after the other, like sort of like a round robin. It says you go, you go, you go, you go kind of stuff. Both can still make progress at half the rate, right? It's acceptable for most things, and you're still happy. But if you give me 1 million and I want to schedule between all the million, I can say you go, and then next one, next one, next one, next one, next one, and all. Eventually I'll get back to you, right? In that case, no one is happy because it takes you a long time to get anything done, right? So operating system is not trying to solve that problem. So if you overload the machine beyond what is sanely possible, then things will fail. And there are things like the long-term scheduler which will try to protect you, but that's not what their goal is. It's trying to protect you from normal usage to have a useful system. And for the most part, systems are useful. I mean, we use machines which are scheduling different processes and all those times, right? But it's not a panacea. So as you might have imagined, the short-term scheduler is trying to make these processes run between the different different queues. So it must be fast, right? It's trying to decide what to run next. And it's doing this in the order of milliseconds on a machine. So if it sits there and ponders for a minute to figure out what to run next, right? It's not good, because all the time it's trying to decide which to run next is wasted time. It's not making any useful progress. It's trying to make decision. So you want this scheduler to be as quick as possible and move on. Whereas the long-term scheduler is trying to look at the overall how the system is proceeding. So it can actually sit down and ponder for a little bit, because it's trying to make a decision which affects for a longer term, right? And the short-term scheduler, you want it to make decisions frequently, because if you don't make decisions frequently, the system does not respond to your needs quickly. But if you do it too quickly, then your overhead comes into play, right? If it takes you 1 millisecond to make a decision, right? And after making a decision, if I let you run for 10 milliseconds versus 100 milliseconds, right? The overhead gets amortized for different levels for different systems. right? So it's a balancing act. It's trying to say, okay, do I want it to be extremely responsive, in which case I want you to interrupt me, I want you to make decisions very often, right? But in that case, I'm spending too much overhead. And that's a parameter you're actually messing with for your homework project, right? You're changing the number of times that the operating system can be interrupted from 100 to 1,000 times a second, right? Making it one way makes it more responsive, but you pay a cost in high overhead. And the last point, so this brings up the issue of CPU bound and IO bound processes. And as we'll see later on, the schedulers tried to differentiate these two and tried to be different to both of them. The idea is, if you're IO bound, you are doing some processing and then you're waiting on IO for a long time. And if you're CPU bound, you're computing something, so you're using all the CPU cycles that I give you. So if I give you some CPU cycles, you'll use it all, right? And there are different processes which have these different characteristics. Typically, IO bound tasks are, web servers or something like that, or your interactive applications. Your word processors and all those things are IO bound because they're waiting for you to type in something. You type in a key, something happens, and then it waits for your backend call, right? Whereas a CPU bound process is, say, computing the pi to the nth degree or something, right? So depending on what the goal of the operating system, it may prefer one over the other. For example, in your in a laptop setting, right? What would you prefer, the CPU bound or the IO bound process? Which one would you like to schedule often in a laptop kind of setting? Does anyone want to take a stand? Yeah, your sense was IO bound, right? So you'd probably want to do IO bound just because you want to make it look snappy, right? But if you're running a server, you may want to give more to CPU bound processes. Again, there's no magic thing which says like, this is the answer. But sort of, you kind of weigh these things to figure out what should happen, depending on what your goal is, right? So this brings up the topic I want to cover before we leave for the day. So in the state diagram, we had all these different states. You are running, and then you kind of go into the next state, right? So to make you go from one state to the other state, you're changing the context. You're changing the context from running to waiting or what have you, right? And that's the process of context switching. So the context switching is you are running, you have the CPU, you have all the you have program counter, registers, and so on, and I want to stop you and then freeze what you have and then unfreeze some other process and let it run, right? So the thing I want to do is I want to save all this. So at this point, your process freezes, right? The OS comes in, it saves all the state for the running process into its PCB, because the PCB has structures for all the stuff, right? So it figures out what the program counter was, it figures out all the values of all the registers for that process, saves it into this PCB, saves all the other sections, right? And it may have to wait for I/O and all to finish, depending on what it's trying to do, and then reload the PCB for the next process. So it goes ahead and loads all the program counter for the other process, registers for the other process, brings all the stuff that it had before it was frozen back online, right? And then makes it run, right? From a program perspective, you don't notice a difference. You don't notice anything happen, right? You are merrily running along for a while, and then you don't have CPU for a while. You can't actually know that because you don't have CPU to know that you are not running, right? And when you come back, all the registers are back where they are. Everything is how they should be, right? And you keep going, right? So is that true? Is that a way for you to actually figure out something happened, or can you make it completely transparent that you don't notice that something was amiss? Yes?
So, like, if I'm using my personal computer and I'm listening to like iTunes or something like that, and I'm surfing the web at the same time, is there there's just constantly this switching mechanism? So I guess it does. You can't really tell.
It's constantly switching. As long as it has enough resources, you won't notice, right? If you have a really powerful machine and you're listening to iTunes and you're watching a video and you're doing fine, it's doing this switching so fast that you don't notice, right? But if you don't have like a screaming machine like that, right, you would notice. You would notice that some things, your iTunes will freeze. You know, depending on your operating system, you may see a spinning ball or something, right? It's not getting enough stuff, right? One other place to notice is your little clock on the top or bottom, depending on your operating system, right? You may notice that your clock, if you have your clock running on a machine, progressing quite nicely every second. Sometimes it will freeze because something is happening. You're opening iTunes, and so one of the things you'll notice is I'm trying to make the video of this class in iPod format and in HD format, right? So if you're playing high definition, you are completely killing most normal machines. Right? If you're playing that, you'll notice that all kind of stuff will happen. Your clock will stop, your mouse will stop, your things will stop, and I don't know if you noticed it, but if you haven't, you'll notice it, right? So, like I said, operating systems can't do magic. So if you kill it, then you will notice all this stuff. And the other way to notice it is through timing, right? And that's what I'm asking you to do for your homework project, right? You don't know that you're idle, but you know that if I do something for a second, right? And I look at my wall clock and I say, okay, now it's some time, and I do something for a second, and then I look at the end time. If they don't match appear to be 1 second, then I know something like this happened, right? That's what you're trying to do for your homework project. So I'll stop at this point. So I'll ask, I'll let you look at the homework project. If you have any questions, drop by, send me email, or we can talk in the next class.